All right. So yeah, welcome to Intermediate Competitive Programming Track Workshop 4. Today we're going to be covering dynamic programming. So on the agenda today, we're going to start off with our raffle, and then we're going to talk about states and recursion, and also relate this briefly to last week. Since there were a lot of conflicts last week, a lot of you guys weren't here, so that will also be an opportunity for you to kind of get a teaser of what last week was like. And then we're going to get into the meat of today, which is we're going to be covering dynamic programming and kind of the two main ways of implementing it. And then we'll be going over 3 example problems, and then we'll end with the Kahoot. All right, so let's begin with our content today. So we're going to go over states and recursion first, which to many of you will probably be more of a recap. So if you're taking CS32 right now, you'll be familiar with recursion, which is what we're learning right now. And also, if you came in one of the previous workshops, you might have also encountered recursion in the form of depth-first search. So just as a reminder, recursion is the technique where a function calls itself. So for example, if we want to calculate the factorial of n, we can do this by calculating the factorial of n minus 1 by calling the factorial function on n minus 1 and then multiplying by n. And since this goes recursively downwards, we need to have a base case to tell it when to stop so that it can go back up. Otherwise, it just keep going down forever, and then that wouldn't be good. And we'll also briefly go over the concept of states. So last week, we played a variety of games. So here's just a simple game where 2 players, Alice and Bob, start with 12 stones. And then they take turns, and each turn they can remove either 1 stone, 4 stones, or 7 stones. And then the last player to remove a stone is the winner. And kind of the main idea for this type of problem is that we want to consider how many stones there are as kind of the state of the game. So at the beginning of the game, we start out with 12 stones. So the initial state would be having 12 stones on the board. And then the first player to take a turn can reduce the board state into 11 stones, 8 stones, or 5 stones by taking either 1 stone away, 4 stones away, or 7 stones away, respectively. And then on the second turn, the next player would reduce the board state down to an even lower state. So by calculating each of these states, we can kind of enumerate all the possible possibilities of how the game can progress from the beginning until the end. And in this way, we can calculate which states are winning and which states are losing and figure out whether a player can force a win or not. So if you look here, here's just a very simplified version of the state after the first 2 moves. So can anyone tell me if we try to list out the entire state diagram where we consider every single possibility for the other branches as well, how many total, including the starting state, how many total unique states are possible in this game? There are a lot more than just 2 states. So you might be thinking of winning states and losing states, but here I'm referring to the state as just how many stones there are. Yeah. Does 0 count as a state? Yeah, so 0 is also a state. Does anyone want to take a guess? 8's a good guess, but there are actually 13 total states, and you can get to all of these states. For example, if you start at 12, it's possible that they keep taking turns only taking 1 stone away. So you'll get the state of 12, 11, 10, 9, all the way down to 0 for a total of 13. And the takeaway here is that although this branching diagram might get really confusing and that there could end up being a lot of states, the number of unique states is not actually that many, which makes calculating it really simple if you keep track of how you can transition from a unique state to a different unique state. And this is kind of the core idea of dynamic programming. So what is dynamic programming? Dynamic programming is essentially the idea where we can break down a larger problem into a bunch of smaller subproblems, and we can use the results from calculating the subproblems to calculate the large problem. So this is very similar to recursion. So if, for example, if you're familiar with merge sort, kind of the idea is that you want to sort half of the array at a time and then merge everything back up together. And you might be thinking that this is exactly the same thing as dynamic programming, but there are some added techniques that we use in dynamic programming to achieve speedups in our code. So for example here, just take the simple example of the Fibonacci sequence. So this is probably familiar to most of you guys, but it's an example of a sequence that uses recursion. So for example, the base case it's just 0 and 1, and then to get to the next term in the sequence, we add the previous two terms. So for example, the Fibonacci sequence is just 0, 1, 1, 2, 3, and it goes like 5, 8, 13, and it just keeps adding the two previous terms. So if we want to code this using recursion, a really simple idea would just to be have a function that returns the nth Fibonacci number, and then for the base case, we just return the value of the base case. And then otherwise, if it's not the base case, we can know that we can calculate the Fibonacci number by adding the two previous Fibonacci numbers and returning that. However, if we draw out what types of calculations are done in this case, even for something as simple as calculating the fourth Fibonacci number, we'll realize that since it's not a base case, it'll try to calculate the third Fibonacci number and the second Fibonacci number. And then for each of those, it needs to calculate more Fibonacci numbers. And then it calculates a lot of Fibonacci numbers, even though if you were to just add them up like normally, you would just do like 0, 1, 1, 2, 3, which is a lot simpler. And the bad thing here is that like it almost doubles every time, because for each Fibonacci number, it needs to calculate 2 more, and then below that it needs to do 2 more as well. So you end up actually using an exponential amount of time to calculate your nth Fibonacci number. So this is obviously really bad. So our naive version of just using recursion directly doesn't actually achieve our desired goal in an efficient manner. So how can we still use recursion without running into this issue where we keep increasing our number of states and like doubling it and creating more and more? And the way that we can avoid this is by storing the values that we've already computed. So since in our recursion for the Fibonacci sequence, there's a lot of repeated calculations of the same Fibonacci number. If we instead store the Fibonacci numbers that we've already calculated, when we encounter again, we don't need to go through the whole recursive process to recalculate it. We can just use our stored value and return directly. So we can just create an array of size however large we need to fit up to our nth Fibonacci number, and then we store the values that we've already calculated. And before we calculate a new value, we first make sure that it hasn't been already calculated so we don't waste time recalculating things that we already know the answer to. So for example, here we can turn our recursion into a slightly different form of recursion, where now we have an additional array outside of the recursive function. Here we just called it fibmemo, short for memoization, which is this idea of storing the values that we've already calculated. And every time when we return, first we check if it's a base case. As normal, we just return the value of the base case. But if it's not the base case, we check if we've already calculated the value inside of our memoization array. And if we've already calculated it, we can skip the step of calculating the new value. So here, if the value is not 0, that means that we've already calculated it. So we completely skip that step and we directly return the value that we've already stored in our array. And if we haven't calculated it, then we do need to still go through the recursive process of calculating it. However, if you've ever calculated the Fibonacci sequence by hand, you're probably not doing this approach where you're calculating from the biggest number and going down recursively and storing the values that you've already calculated. You probably just start directly from the base case and work your way up. So this is another way that you can do dynamic programming, and you avoid the issue of recomputing values that you already know the answer to. And for this, we call it the constructive approach, and it's also known by the name of tabulation. So we start from a base case, and then we perform a state transition that moves us from our base case to a larger state. So for example, for the Fibonacci sequence, our base cases are the 0th Fibonacci number is 0, the first Fibonacci number is 1, and then to get to the next Fibonacci number, we just add the two previous ones. So for example here, since we know 0 and 1, to get to the second one, we just add those two, and we get 1. And then we can keep filling out this array just the normal way that you would list out the Fibonacci sequence. So what this looks like in code is just, we can still kind of use like this memoization array, except we don't actually need to go down to calculate it. We can just directly fill it up from the bottom up. And we start with our base cases, and then we loop from the cases that aren't our base cases, and we just calculate the values depending on the previous two values. And in this way, since we're going from the bottom up, by the time we get to the big case, we know that we've already processed the smaller cases. So the issue with memoization is that we need to know the value of the smaller cases, but we might need to calculate those first. But when we go from the bottom up, we've already calculated the smaller cases so that we can just use those values directly rather than having to recalculate them. So this is kind of the two main ways of avoiding this recalculation issue when doing recursion. So kind of what this looks like in terms of visualizing what the computer is doing. So in the tabulation case, it just goes directly from the bottom up. But for the memoization case, it needs to spend time calculating the subproblems before going back up and rebuilding the large answer. So you might be wondering, like, what's the difference between these two? Like, can I use either or like, do you always want to use one versus the other? And the answer is that it depends. So for memoization, like obviously the implementation technique is that you use just recursive function calls, but you store the values that you've already calculated, so you don't need to calculate them again. And generally, when you first approach a problem, this is the more intuitive way to approach it. And it might also be more natural to code in this way. But the tabulation way of going from the bottom up is also really convenient in a lot of cases, where it's a lot easier to transition from the values that you already know and just keep building a larger value. And especially once your states get really complicated, for example, if there's more than one variable you need to keep track of in your state, a lot of the times using this bottom up approach is simpler to implement. And in terms of speed, usually both of these will run in a fast enough time. And it's hard to say which one will definitively run faster. The issue with memoization is that it needs to go down before it can come back up. So it might need to do kind of twice as much work. But the issue with tabulation is that you are computing every single value up until your current value. And sometimes that's not necessary, and you can skip some of that computation if you were to use the recursive approach using memoization. So it's pretty dependent, but generally, you can choose either or, and it's just whichever way you think fits your problem better and is easier for you to wrap your head around is the one that you can use. And yeah, again, just the entire idea of how dynamic programming works is that we want to, in order to calculate our entire big problem, we want to figure out some way where we can use the values of smaller problems and kind of combine them together to get our big problem. And we can use this either iteratively with tabulation or recursively using memoization. And either of these approaches are perfectly good ways to calculate our final result. All right, so does anyone have any questions here? Okay, let's get started with our first problem of the day. So the contest link, as usual, is here, and you can go look at this problem on the Caddis platform itself. And I'll also put this up on the board for anyone who would prefer just reading it on the board. So I'll give you guys a few minutes to read the problem and kind of figure out what it's asking. All right, so hopefully everyone's had a chance to read the problem. I'll briefly summarize it again here, just off the slide. So we want to construct a long plank of length n, and we can do that by combining smaller pieces of lengths 1, 2, and 3. And we want to figure out how many total ways we can combine those pieces to create our long plank. So if you direct your attention to the slides, you'll see kind of an illustration of what this problem means. So the number of ways to combine your 1, 2, and 3 meter pieces to make a 4 meter long plank. There's 7 ways to do it, and they're illustrated here. So for example, we can use just 4 1 meter pieces glued together, or we can use a 2 meter piece and 2 1 meter pieces glued together, or 2 2 meter pieces, and so on and so forth. Also note that the order that you use the pieces counts as a different way of using it. So if we use a 2 meter piece and 2 1 meter pieces, it's different than using, say, a 1 meter piece, then a 2 meter piece, then a 1 meter piece. So the order does matter. So kind of the first idea that we want to use in order to tackle this problem is that we want to be able to reduce our problem into a smaller subproblem so that we can use our ideas of recursion and dynamic programming to approach this problem. So does anyone have any ideas of how we can kind of reduce our task of finding how many ways there are to get a really long plank and to perhaps somehow into smaller planks? All right, so the idea here is that if we want to reduce our problem of finding a really, the number of ways to find a really long plank, we can reduce it to a smaller plank by just removing the first wooden piece. So if we remove a piece, then the plank will be shorter, and that makes it so that we can use the previous values. So for example, the kind of recursive way that you could think about this is if I want to make a plank of length n, I can do casework on the size of the first plank, first piece. And if the first piece is length 1, then I would be calculating it on a plank of length n minus 1. If the first piece is of length 2, then I would be calculating it on a plank of length n minus 2. And the same for if the first piece is length 3. So in this way, I can count the number of ways to do it for the plank of length n by just adding up the 3 smaller cases. But then, of course, whenever we implement this in a recursive way, we do need to write a base case. So we would need to consider what our base cases are, and also we would need to add memoization, because otherwise we would run into the exact same issue as with the Fibonacci sequence, where when we try to calculate our cases, it kind of calculates 2 every time, except in this case, it's actually 3 every time. So it kind of get like triples every time, and that's obviously going to take a really long time if you try to calculate a large value of n. So we need to use, we need to store all the values that we've already calculated to avoid recalculating them. But also, since there's 2 ways of doing dynamic programming, the probably easier way in this case is to just use the tabulation method, which is the bottom-up constructive approach. So we can just start directly from the base cases and then figure out what the state transition we need is in order to go from the base cases to build into a larger. Okay, so I'll hand out worksheets that kind of have the template code already written. And if you guys want, you can think about how you can fill this in. Yeah, generally the top-down way and the bottom-up way can look pretty similar in a lot of cases. So I'll put this top-down approach here as well that you can use as reference. All right, so does anyone want me to kind of help you guys out individually, or would any of you guys also just want me to present the solution? I guess you can raise your hand if you want me to come over, or just like give me a thumbs up if you're ready to move on. Right, I think I'm seeing mostly thumbs up. Would anyone like an extra minute to kind of think about it a little bit more? All right, I will go over the solution now. So, yeah, so this is kind of what the template code looks like. And if we fill it in, we can do so in this way where we fill in what our base cases are. So for example, the answer for if our plank is going to be of length 1 is just 1, because there's only one way to do that, which is use the length 1 piece. For a plank of length 2, we can do that in 2 ways. And a plank of length 3, we can do it in 4 ways. You can also start from a base case of 0 rather than 1 if you wanted to. And the number of ways that you would create a plank of length 0 is also just 1 way. And you would do that by doing nothing, which is kind of a weird way to think about it sometimes. But a lot of the times using a base case of 0 can make your calculations slightly simpler. And then regardless of which base cases you choose to use, after you finish listing out your base cases, you need to start from the next value and then calculate the values for all the values after that. So this might kind of look like sort of like a proof by induction almost, where you start from the beginning and then afterwards you can just fill in everything else, like dominoes knocking each other over. And the transition here is that in order to get to the next value, we just add the 3 previous values. Does anyone have any questions? All right, let's move on. And next we're going to go over a very similar problem, but this will have a slightly different trick, which will be a little bit different from the previous one, but it'll still roughly be the same thing. But then our third problem will be significantly different, although it might not seem so at first glance. So for this problem, it's very canonical. So kind of the idea here is that we're going to calculate the number of ways that we can, actually not the number of ways, we want to figure out the minimum number of coins we need to reach a target sum. So for example, like if you're at a store and you have like a lot of pennies and a lot of nickels, a lot of dimes for some reason, I don't know why you would have a lot of coins, but let's say you want to pay for something that's exactly, let's say like 35 cents. You wouldn't want to pay with like 35 pennies because that would take forever to count. So you want to use the least number of coins to reach your target. And here we have a variety of different coin sizes depending on the input. So it might be like, for example, just like it might be like really weird coin amounts, like maybe like 3 cents, 6 cents, and 7 cents. And yeah, so the idea here is that you just want to figure out how you can get the minimum number. And then also, if any of you guys are familiar with counting money, normally the way that you would get the least number of coins is you would just like take the biggest denominations. So for example, like to get to like 35 cents, you would just take the quarter because it's big, and then you would take the dime because it's like the next biggest, and you would get to 35 cents. And that's kind of the greedy approach to this problem. But for this, it's not actually going to work out in all the cases. So for example, let's say we have a 2-cent coin, a 6-cent coin, and a 7-cent coin, and we want to make a target of 8 cents. We can't do that by taking the 7-cent coin because there's no 1-cent coin, but we can do it with the 6-cent coin and the 2-cent coin. So we will have to use a slightly more advanced technique than just taking the biggest one every time. So this is why we need dynamic programming. So yeah, if we want to think kind of with the idea of dynamic programming and with recursion, so we want to know what the minimum number of coins needed to reach some value is. We want to first determine how we can reach smaller values first. And then we can, once we know the values for the subproblems, we can kind of build back up into our big problem, which is kind of the key focus of today. It's always we want to first figure out how we can reduce our problem into a smaller problem first. So this part is very similar to the previous problem of the plank, where we can reduce it to a smaller problem by simply removing one wooden piece. Here, instead of removing a wooden piece, we can just remove one coin. So now if we do casework on, like, let's say if we remove a 2-cent coin, a 3-cent coin, or a 4-cent coin, we can then try to calculate what the optimal solution is for our subproblems, and then use that to calculate our new value. So for example, if I fill out the base cases here first, where like the number of ways to do it for, like the best way to do it for the 2-cent target, 3-cent target, and 4-cent target is to just use the 1-cent, the 2-cent coin, 3-cent coin, 4-cent coin respectively. So you only need one coin for each of those. How would you calculate the value for the 5-cent coin, 5-cent target? Also here, I kind of used a trick here where I put the value for the 1-cent coin as just 999 because it's impossible to get to the 1-cent target. So if you ever like calculate your values and you want to find the least number, if you see like a really big value like 999, you know that's not the correct way to do it. So you can kind of just ignore that. That just means it's impossible. So I'll first kind of illustrate how these yellow boxes are the subproblems that are necessary to calculate the green box. So the 3-cent target is the idea of to reach our 5-cent target. If we want to use a 2-cent coin, then we need to also need the remainder to be 3 cents. And if we want to use the 3-cent coin, our remainder is 2 cents. And if we want to use the 4-cent coin, our remainder is 1 cent. So regardless of which coin we use, that uses one coin. And then for each of the remainders, we want to minimize the number of coins we use for the remainder. So does anyone have any ideas of what the transition would be from these smaller problems to our big problem? I'm just going to go ahead and tell you guys the answer. So we use one coin to use either the 2-cent coin, 3-cent coin, or 4-cent coin. And we want to minimize the number of coins we use for the remainder. So to do that, we just take the minimum value of the 3 subproblems of the cases where we use the 2-cent coin, 3-cent coin, or 4-cent coin. So in like this illustration here, the remainder of 1, 2, and 3, the best way to do that is you can reach one of these values by using a 1-cent coin, by either getting the remainder of 2 or 3, and then we can just use the 3-cent coin or 2-cent coin to fill in the rest. And then as we go upwards, kind of the idea is that we again look at the 3 subproblems, take the least value, and then add 1 to get to our next one, because we need 1 more coin to increase upwards, and then we want to take the minimum of the previous ones. So here it's 1, 1, 2. We take the minimum, it's 1, add 1 to get 2. Here it's 1, 2, 2. We again take the minimum of 1, add 1, and then get 2. And then for this case, it's 2, 2, 2, so the minimum is 2, and then we add 1 to get 3. So does everyone kind of get the idea of why, if we know the values for the subproblems, we can take the minimum, and that will help us to get the new minimum value. All right, so if you want to try coding this, so for this one, this problem is not up on Caddis. So you can just try this out for kind of some hard-coded test cases. So let's say we want to reach a target n of 21, and then the coins that we have are 2-cent coins, 3-cent coins, or 4-cent coins. And then we want to figure out what the minimum number of coins we need in order to get to our target. All right, so hopefully everyone's had a chance to think about this problem. I'll go over the solution. So again, we can kind of hack our way around the base cases by just setting the base case of 1 to be a really big number so that it doesn't get used later on. Normally, when you were to calculate this, you'd probably want to set it to, for example, a negative number and have an if statement to check for impossible values. But this works fine in this case. And then in order to do the transition, we take the minimum of the 3 cases where we use the 2-cent coin, 3-cent coin, or 4-cent coin, and then add 1 since we needed the 1 coin to do the 2-cent coin, 3-cent coin, or 4-cent coin. And kind of the way that we can get, since we know that there's only 3 coins, we can just hard code it with nested min statements. But normally, if you don't know how many coins you have, you would also need another loop to go through every single possibility. And also note that since in each state transition, we can use the 2-cent coin, 3-cent coin, or 4-cent coin. It's possible that, like, for example, we just keep using the 4-cent coin over and over and over again. Like, for example, if our target were to be 100, that would be the optimal solution. So it's very convenient that we can use each coin an infinite number of times. So then we can just do it in a very simple way like we've done here. This will change in the following problem. All right, so if there are no more questions, let's get to the next problem.
Okay, our final problem of the workshop today is going to be this problem C, exact change. If you want to look at it, you can go to the link, read over the problem, but the problem statement is, I'll give you guys like 2 minutes to read the problem and then I'll explain what it's saying. Okay, hopefully that was enough time just to get the gist of what the problem is asking. So let's just go over basically what it's saying. So the problem is you're given a bunch of different bills and coins of varying values VI, and your job is to figure out what is the least number of bills that you would need to pay for an item of a given cost. And so it's basically like you're at a store and you have a bunch of different bills and your goal is to not overpay too much for an item. So you have to at least get to the value of the item in order to pay for it, but you don't want to spend more than you have to, and you also want to use the minimum amount of bills that you can and still afford the item. So as an example, let's say that you have these $3 bills with you. You have a 5, a 10, and a 20. And what is the least value and number of bills that would be required to buy an item of cost 14? Can anybody answer that? It's pretty intuitive. It's just like you're at the store. How would you pay for a $14 item with these three bills? The 5 and the 10. So exactly right. You'd use the $5 and the $10 bill, you know, and that's pretty intuitive for us since we work with money all the time and we're used to paying things at stores. But how would we tell a computer that we're trying to minimize the value, but also the number of bills at the same time? And so this is where dynamic programming comes in. And in this case, because we're trying to minimize both the value that we're trying to pay and the number of bills that we want to use, we actually need a two-dimensional dynamic programming approach. So instead of just using one array this time where we build up a bunch of values, we're actually going to be using a two-dimensional approach. So our job basically is given a bunch of different values. So you have a bunch of bills and you don't know what each value is. You want to add them all up so that they're greater than or equal to the cost while keeping the minimum number of bills and value. So there are these three main things that we're trying to basically keep track of. For each of the values up to the cost, as we do in dynamic programming, we build up from the subproblems. So we're going to work from value equals 0 all the way up to our cost and even beyond. And we want to determine the minimum number of bills required to reach each of those values. And so that's kind of our columns in that table. And then for our rows, the second dimension that we're building up is usage of each bill. And so for the first row, we're going to consider only using the first bill. And then as we go down, we're going to consider excluding or including the use of the next bill in our solution or our final combination of bills that we'll use to pay for the item. And so using both of these concepts, we then will be able to determine the minimum bills that will be required to pay for a value of the given cost. And that's kind of like the last row of our table once we've considered using every single bill and we've considered how many bills would be required to reach each value up to our cost. So to make this more defined in math terms, we're going to let this value b subscript m comma v be the minimum number of bills using only the first m bills whose face value sum up to v. So we'll go over this more, but basically you want to start at the point where bm0 equals 0, which is to say that using any amount of bills to reach a value of 0, it takes 0 bills. And this represents our base case. So we know that to pay for something that's free, you don't need any bills. But now we need to work up via our transition step to higher values and greater number of bills. So we basically want to build up this table of increasing values and of increasing bill usages by expanding out each row and then each column. And so, like I said, each column will represent a different value that we're trying to reach as our target amount, and each row will represent a different bill that we are adding to this setup. So for instance, if we have these 4 bills on the top right, we have a $1, $3, $4, and $2 bill, kind of weird values, but their numbers are arbitrary. If you build up the table and you reach the first, if you fill out the first 3 rows, you'll see that you get these combination of bills in order to reach each value. So with dynamic programming, we're always going to assume that we know the answer to a subproblem in order to solve the answer to the main problem. So assuming that dynamic programming has filled out this table and we've reached this point, we're now on the m equals 4 bill, which is a value 2. We are going to take these values and we're going to check if there's a way to reach the value that is the value of the bill columns left and 1 row up plus 1, which is a kind of confusing concept, but it's the same idea that we were using before with the plank and with our coins, where we're checking if we have an answer to a subproblem, and then we're going to add the mth bill to that value in order to reach this new value. And because we're using this 2D approach, we have to check the row above and columns to the left. And we will go over that now. So this represents the first m-1 bills. So we're using our $1, $3, and $4 bills. And we've already filled out the table. So we know exactly how many bills and what values it will take to get to those values. And so this row represents, if we want to get to 1, we only need this one $1 bill. If we want to get to 8, it takes the 1 and the 3 and the $4 bills. And so our transition step here, once we have this much of the table, is to check the values that are, in this case, $2 means we're going to go 2 columns to the left and check if we can make the sum of money that's $2 less. And then we're going to check the row above, which is using all the other bills except for the current bill that we're checking. So using our $1, $3, and $4 bills, can we add a $2 bill to that to reach each of these new values? And so we're going to go through each column in order and simply check if we're able to do that. So it takes 0 bills to reach $0. And since we're using a $2 bill here, we can add $2 to that to get this value of 2. I kind of skipped over 0 and 1 because we can't add 2 to anything to get 0 and 1. And then we just continue on. So the next thing we're going to do is go 2 columns to the left and up 1 from this cell. And so we'll see that using our nth bill of $2, if we add it to our $1 bill to reach 1, it now takes 2 bills to reach the value of 3. And we can just keep going. So you can see that we can't reach the value of 2 using our $1, $3, and $4 bills. So that's why it says NA. You can use an approach like before where you set it equal to a really large number to represent that it's unreachable, or a negative. Either is fine, but basically there's no way to reach $2 using our first m-1 bills. And so now using the nth bill, there's no way to add to that in order to get to $4. So we just say that it's unreachable. But then when we get to $3, we can see that we have a $3 bill, which we use to get to 3. And so we add 2 and we put that in our new cell and we get $5 by adding our nth bill. And we keep going. We do this for every single cell in the column, in the row. And you can see that whenever there's a not applicable, we can't add a $2 bill to that to reach a new number. And so it continues to be that. And you end up with this new configuration of ways to reach all these different values. Does anybody have any questions about how that approach works? So now is kind of the part where we try to answer the question. Knowing that we've built up our whole table here of following this approach where we started in the first row and we worked our way through, and we finally got down to the mth row, or the final row of using every single bill, and we've reached all the way up past the value which we're trying to get to, then our goal is to figure out what is the minimum number of bills we need to reach that value. So in the table here, we included the actual dollar amounts that the bills were so that you could help visualize what we're paying with in order to reach those values. But all we really care about is the number of bills. So regardless of what their values are, we're really just trying to find what's the minimum number in every column in order to reach that value. So for example, in the value equals 7 column, you can see that there are 2 ways to get to 7 using our $1, $2, $3, and $4 bills. You can either use a 3 and a 4, or a 1 and 2 and a 4. And we got these 2 different approaches by 2 different parts of the table and adding the $4 to the $3 and then adding the $4 to the $1 and $2. And either are applicable here, but we're just interested in what is the least amount of bills we need. So when we take this value, B of MB, which we said will represent our minimum number of bills to reach a value B with M bills, we just take the minimum of that column. And when we're actually coding the approach, we'll not have the actual values and we'll just be taking the minimum as we go throughout. And so this number would really just be 2, that one would be 3, and then this one will be 2 because we only need 2 bills in order to reach that number. And so if we were trying to reach a value like 7, for example, we would see that our answer would simply be 2. We only need 2 bills to get there, and we found it by just filling out our table and then checking what the minimum value for that column is. So to formalize our answer, we're letting B of MV be the minimum number of bills using only the first M bills whose face value sum to V. We started by setting the first column equal to 0, which is to say that it takes no bills to reach a value of 0. And then we either use the mth bill with this face value of F, or we don't. And that's what we do each row. When we build up, we add a new bill on and we decide if we're going to use it or if we're not going to use it. So if we use the bill, the minimum number of bills for a given value V is equal to B of M minus 1 of V minus F plus 1. So I know the math notation might be a little bit confusing, but can anybody tell me what the value of b m minus 1 b minus f would represent in this case? I kind of went over it in my explanation, but just to check that the math translates to the problem, can anybody say what that value represents here? Okay, no worries if not. Basically, this just represents the value in the cell that is like F column still left, which is the value of our bill, and one column up and one row up. So it's exactly what we were doing before, where we go over the value of the bills columns and then up a row in order to check if we can find a way to reach that value. And then we add our bill to it, which is to add that mth bill and that F face value. And we get one row down and F rows over, F columns over in order to reach our new value. Now, we either use the mth bill or we don't. And in what case would we not use our mth bill? The answer is basically if there is no valid value in the cell that is m minus 1 and b minus f over, then there's no way to reach it. So we're not going to include it, and we'll simply take the value of b of m minus 1 b, which is to say that we can't include that bill. So let's just imagine that we're not using it and we take the value directly above it. However, if there is a valid value, the time that we would not use that bill is by taking the minimum of the two different answers, and that will be our solution because we're trying to minimize the number of bills. So if adding that bill is going to just increase the number of bills that you're using unnecessarily, then you can simply choose not to include it. So that's all a little bit confusing maybe, but essentially we're going to build up this table starting at the first row. And the first row is the easiest one to fill out. So can anybody tell me how you would fill out the first row of our table, aka only using the first bill? If you only have one bill of some random value, can you tell me what this row at the top of our table would look like? Yes. Yes, exactly. I didn't put it on the slides, but that is exactly the answer. You basically just fill out a 1 where you can use that bill in order to reach that value. So you just pay the exact value, and any other value is unreachable because you don't have access to any of your other bills yet. So you just put them at some value that represents that it cannot be reached. So now that we've built up the intuition for how we go about filling out the table, how do we answer the problem? So if we go back to the problem statement, what it's asking is what is the minimum value that we need and the minimum number of bills in order to pay for an item of cost C. So if our item is of cost P, then basically we're checking to find the lowest value V such that we can pay for the item, aka that there is a value in our final row of the table which represents a method of paying for a value V. And so we check our cost P in that column, and then if there's no valid way to reach that cost, then we need to pay extra. We need to waste some money, and so we're going to keep checking outwards until we reach a value for which we have a valid way to reach, and then that will be our two answers, which are the value and the number of bills required to solve it. So for example, if we filled out our whole table and we ended up with this as our final row, which is to say that using all of the M bills that we were given, this is the minimum number of bills that we require to reach each of the values given by the column number. So in this example, we're given a $2, $3, $3, and $10 bill, and these would be the values that we find out. So you can see that, for example, to get to 8, it would take 3 bills. We use our 2, a 3, and a 3, but then to get to 10, it would only take 1 bill. So if our target cost P is $7, can anybody tell me how we would check what our answer is, given this is our final row in the table, aka our full fleshed out solution, and a target cost of 7? Okay, no worries. So basically, you're just going to go to the seventh column and check if there's a value there. And if there's not, for example, here, the value is NA, which is to say that there's no way to get to $7 with our 2, 3, 3, and $10 bills. And so we have to be able to afford the item. So we need to check to the right of this column. And we keep going until we reach a column that has a valid value. And so here we can see that our answer would be, we have to pay $8 and use 3 bills in order to pay for our item of cost 7. And you can think about using these 4 bills, that would intuitively be using the 2, the 3, and the 3. And because of those values, we can't reach 7, so we have to overpay by $1 and use these 3 bills. And our goal is to minimize the value first rather than the bills. So instead of continuing and going and seeing that we can use a 10, which is only 1 bill, we want to minimize the amount that we're overpaying. So we pay $8 and we use 3 bills, and our final answer is going to be 8.3. Because the question asks you to output the value that you're paying and the number of bills that you're paying for the item of cost C. Okay, so if you flip over your worksheets, on the back, there is a template code for this problem. It's a little bit off. I changed a couple of things, but this is the current version. So if you could just take a few minutes, look at this code, maybe try to identify how this is implementing the problem that we just talked about, and then see if you can just get an idea of how to fill out these blanks. It's a little bit tricky. This is definitely a harder problem. If you ever heard of knapsack dynamic programming, this is basically that problem, and it will come up in future courses, maybe like CS 180. But if you can just try to get an idea down for how you would solve this problem. Basically, this is all the setup for how we implement the array itself, and we get this 2D structure. I just use the vector vectors, and then I use these values Vmax and Vmax to represent our like impossible, unreachable ranges. Vmax representing like, in the problem statement, you're given a max of 10,000 bills. And so if you use 10,001, that's impossible. And so that represents that we can't reach that value. And this initializes the first row. I mean, the first column to 0, like we said, is our base case. And it initializes the first row so that the value at our first bill is equal to 1 and everything else is still unreachable. And then in the for loop, we're basically trying to set each of our values in the table according to the formulas that we have, where we're minimizing the number of bills required to reach that value at each column. And then at the end, you just want to print out what our answer should be by that last slide, where we're checking the cost at that column and then moving right. So I'll give you guys a few minutes just to see if you can tackle this, and then I will go over the solution. Okay, I know that was not very much time. I'm sorry. This took me a while to work on, and hopefully you can work on it more this week and kind of figure out what's going on and solve some more DP problems. But in the meantime, I'll just go over quickly what the solution to these 2 blanks are. So basically, in this first double for loop, we're just going to use our 2 kind of equations for setting the min value of B, and we're going to set B of MV equal to min of itself and of Bm minus 1V, which is to say that if we're not going to include that bill, aka we're using the value in the column right above, then we can just take that value. And we then check if B is greater than or equal to bills of M, which basically means that we're checking to make sure that we're still in the array bounds, but assuming that we can go bills of M, which is the value of our mth bill, column to the left, then we'll check that column and the row above. We'll add 1 to it, and we'll take the min of the current value and that in order to see what's the minimum number of bills needed to reach that column or that value. And then in the second to do area, we're basically just going to start a for loop at the column of our cost target. And then until we find something that is less than Bmax, which is representing our value of infinity or unreachable in this case, we will continue moving right until we find a value which is valid and exists. And at that point, we will just print out the value of the column and the value of our table in that cell in our final row, which will represent the value that we're paying and the bills that we're required to pay that value. And then we break so that we don't output a bunch of other values past that. So little bit complicated, but this is knapsack dynamic programming, if you ever heard of it, and now you know. So that is the end of our official workshop, but we still have Kahoot, so please stick around. And if you can fill out the feedback form, that is greatly appreciated. If you fill it out, you win the chance for a raffle ticket. And if you show up next week, then you can win. And we really appreciate all your feedback. We read it all. But also check out our website. We have info about all of our events and ICPC going on there. And now we'll do Kahoot.